So hello everybody and welcome to today's SEDS online webinar. As always, we would like to thank our sponsors from IAS, which allows us to offer all of these resources free of charge. This includes things like recorded lectures, learning tools, and even some of our virtual field trips. So make sure you take a look at our website to see all the new info that we have up there. Today's lecture is by Dr. Dan Bellin, who is a sedimentologist and assistant professor at Utrecht University. Dan received his master's at Imperial College London and his PhD at the Colorado School of Mines. His research interests include reconstructing depositional environments from sedimentary outcrops to understand ancient sea level change, the movements of sand dunes, and to predict deposition and erosion of ocean bottom currents. So I'll hand it over to you, and thanks for coming today, Dan.
Yeah, thanks a lot, Simone. So as Simone just mentioned, this talk is going to be about my work on sand dunes. So specifically what I'm trying to do is I'm trying to see if I can sort of geometrically link the shape of a dune to its speed. And hopefully throughout the talk, you'll see why that link is particularly interesting. So what I'm really going to focus on is the geometries that are involved. So here's a nice little video that shows sediment sort of saltating across the windward side of the dune. And a lot of work has focused on these types of relationships. So how the wind really interacts with the sediment itself. But what I'm really focusing on is the geometry of this. So really the shape of the dune and the size and all of these things. And they can actually tell you already a lot about the dynamics of the sediment that is involved. So my project regarding this talk is basically already done. So I already finished the paper, but it's currently under review. So if you want to read the preprint, it's published on Earth Archive, and the DOI is here in the top left of the screen. So if you look at this from really essential basic geometric principles, then some things that we can state is that as the wind is pushing the sediment, the speed of any volume of sediment will be proportional to, of course, the speed of the sediment itself, but also the ratio of the sediment that is exposed. So obviously, if you're moving a volume that is only partially exposed to the wind, then that volume will actually move less as compared to a volume of sediment that is completely exposed to the wind. So we can describe that as this equation at the bottom. So U is the speed of this volume. C is the average speed of the moving sediment. And the exposed sediment in this context is essentially the same as the product of the surface area that is exposed to the wind and the grain size. So why the grain size? The grain size basically because we're assuming that the exposed sediment is only the top layer of material, right? So everything below 1 grain size of material is not exposed to the current. So essentially what this equation says is that the speed of any moving sediment volume is proportional to the speed of the moving sediment and the surface to volume ratio. And that's really the key factor that we're going to be looking at. And I believe that this surface to volume ratio contains the geometric properties that are responsible for generating bedforms. So a surface to volume ratio is kind of a quirky property. It depends on two separate things. So it depends on the size of an object as well as the shape of an object. So what you see here is a nice little diagram that shows you how surface to volume ratio actually depends on shape. So if you say that you have a cube that is 1 meter wide, this cube has 6 sides. So the surface area of the cube is 6 square meters. And the volume is 1 cubed, which is 1 cubic meter. So as you double the size of the cube, you don't really change any other properties of the object other than the size. Then you can do the same calculation and you'll find that the surface to volume ratio has halved. Now, this sort of principle that the size relates to the surface to volume ratio is really at the basis of some really fundamental sedimentology. For example, the law of settling velocity, so Stokes' law, really describes the relationship of drag forces and gravity forces, which is directly proportional to this surface to volume ratio. Right, so a larger object has a lower surface to volume ratio and experiences less drag compared to gravity. So it will actually settle more quickly as compared to a small particle like a sand particle or a clay particle. Now, the same can be said for dunes, but in case of dunes, the shape also plays a really important role. And to illustrate this, the first thing that we have to demonstrate is that the surface to volume ratio in terms of bedforms is completely irrespective of the width. And the reason for that is that both the surface area and the volume are both dependent on the same factor of width. So when making this ratio, we're essentially canceling out width, explaining why these bedforms tend to form totally parallel ridges that are uniform in the what I call the current the wind parallel cross section. Right, so essentially we can completely disregard width. We can cancel it out from the equation and use the same factor across these parallel ridges. Now, the second thing to show is that the gradient of the bedform also determines the surface to volume ratio. So if you take any sediment volume that is at rest, then it will always be inclined at either direction, right? Sediment will not form like a tower or an upside down pyramid. It will always form some sort of inclined shape. So you can approximate that by two adjacent right triangles. Now, in this case, these right triangles are characterized by two angles, which is beta on the windward side and alpha on the opposite side. We'll get into later that alpha is actually similar to the angle of repose. But if we calculate the surface to volume ratio in this context, then we find that it's proportional to the exposed surface area, which is the hypotenuse of this windward triangle, divided by the volume, which in this case is the surface area of both of these triangles, which is equal to half times the wavelength, so the entire length of this thing, multiplied by the height. And that becomes 2 divided by the wavelength multiplied by the height over the hypotenuse of the windward triangle, which is actually the sine of beta. So what I've demonstrated here is a little bit complicated, but what I've demonstrated is that the surface to volume ratio in the context of sediment volumes depends initially on the size, so on the wavelength, and secondly, it also depends on the angle. It depends on this this windward angle. Now, if you look back at the initial equation that we had, then we find that the speed of a sediment volume that is driven forward by wind will be inversely proportional to the size as well as the windward facing gradient. Now, I believe that this very sort of simple geometric principle is enough to already explain why this phenomenon occurs so ubiquitously. And the reason for that is really the same reason as why we see large pebbles and boulders on a river channel. So if you've ever seen river channel sediments, they're always very coarse-grained. And obviously this is not because there are no fine sediments in the river, right? The river water is transporting all sorts of sediments, including clay and sand. However, the clay and the sand has such a high surface to volume ratio, it is moving so fast that it will always get removed from the system. And the coarse, slow-moving material will always be preferentially left over. Now, if you look at the equations that I just showed you, then you can apply the exact same principle to a loose, uniform bed of sand. So a uniform bed of sand will essentially move very fast initially as the untilted bed gets moved away. And what remains is a slower, more stable tilted geometry, right? So basically what we're seeing is deflation of this sand and the survival of the slower organization of sediment. Now this seems quite simple, but it's actually different from sort of the dominant perspective on why bedforms exist. Because the dominant perspective really revolves around fluid instabilities. So there's actually many different theories and ideas, and most of them involve things like this Kelvin-Helmholtz instability, which is sort of a train of this turbulent motion of fluid that generates a train of this erosion and deposition across the surface. Now, what I'm saying is not necessarily mutually exclusive to this. I think both of these principles are equally true. But I think the geometric principle is perhaps more fundamentally the reason why this principle would exist. And one argument I have for that is that if this phenomenon, if these ripples and these dunes would be generated by completely turbulent instabilities, then why is it that they form such perfectly regular geometries, right? It's a little bit counterintuitive. Now, in order to add a little bit of credence and a little bit of believability to this geometric perspective, I'm going to perform a really special magic trick. So what I'm going to do is I'm going to estimate or predict the speed at which this dune, this is a high-rise satellite image of a Barkhan dune on Mars. And according to these geometric theories, I should be able to predict the speed at which that Barkhan dune is moving based purely on its shape, right? So we're not looking at time series. We're basically comparing the predicted speed to the time series, so to validate whether our prediction is correct. But what I'm essentially showing is that the shape of the dune is directly related to its speed, and it is related intimately towards this surface to volume ratio idea. Now, to start with this equation, we need to develop a power balance. So we know that every dune is powered by the wind, obviously. So what we can say is that all of the mechanical power of the dune comes from the wind power. So by equaling those two, we can actually get a lot more insight into what drives the dynamic. So the initial power balance that I set up here is that the wind power, PW, is equal to the dune's power, PD, multiplied by the sum efficiency, right? So of course, not all of the wind power is converted into the dune's power. So there's some energy that gets lost, and that is accounted for by this add letter. The equation I use to describe the wind power across the dune is exactly the same as the equation that is used for describing the wind power across a wind turbine. So when you want to calculate how much power a wind turbine is going to generate, you need to look at the kinetic energy of the wind that's moving across the blades. So the kinetic energy, of course, is half times the mass times the velocity squared. And in this case, the mass is dependent on the density of air and the volume. And the volume is also dependent on the wind speed. So what we get is the surface area that is covered by the blades of the wind turbine, multiplied by the density of the air, multiplied by the wind speed to the third, right? So it's wind speed squared multiplied by an additional factor of wind speed. which determines sort of the lengthwise component of the volume of air that is moving across this wind turbine. Now, this very simple equation is used ubiquitously in this field of wind energy, and it really fits almost exactly with measurements. So here's a graph I just pulled from some paper that where they predict the speed of where they predict the power generated and they compare it to measurements, and it lines up super well. So this equation really describes most of what is going on in terms of the physics of a wind turbine. Now, obviously, it tails off towards the top, which is related to the efficiency, but that's not really what we're talking about in this context. Okay, so we know the power of the wind that is moving across the dune, which is half times the height of the dune times its width times the density of the air times the wind speed to the third. So the next thing we're going to do is look at the mechanical power of the dune. So on the windward side, all the sediment is basically moving up and over the brink of the dune, while on the forward-facing side, it is actually cascading down under gravity. So it's not directly exposed to the wind. And the sediment has this tendency to sort of oversteepen across the brink and then fall down under gravitational acceleration towards the ground. So we can use that principle to derive an equation for the mechanical power of the dune. And that would, of course, complete our nice little power balance. So let's say that the dune is, of course, sitting above the surface. So it has the sediment that is on the top has some gravitational potential energy, right? The gravitational potential energy is described as the mass times the height times the gravitational acceleration. And the mass that is moved downwards over time is proportional to this parallelogram that you see at the bottom of this figure. Right, so if the dune is, let's say in T1, it's on the left side and it moves within one increment of time towards the right, then proportional to the speed at which it's moving, it will move this parallelogram of sediment downwards from its brink, so from height h to the ground. And by sort of multiplying the gravitational potential energy with the speed, we actually get energy over time. So we get the power of the dune, which in this context is the height squared. So h squared times the width times the gravitational acceleration times the density of the sediment times the speed at which the dune is moving. All right, so putting both equations together, we get this nice little power balance. And we can start crossing off some factors. So we lose the width again, similar to the beginning of the talk where we lost the width in the surface to volume ratio. We're also losing the width in the power balance. And we're also losing one factor of height. So essentially what this equation said is that the wind speed to the third power is proportional to the height times the speed times a bunch of other things, right? Gravitational acceleration, the density ratio of the sediment and the fluid, and the efficiency of the dune. Now, I've already shown you earlier that we can actually calculate the volume flux of the dune based on these two values for height and migration rate. So it's a very well-known principle. It's sometimes called the Buck-Knowles principle or Buck-Knowles law, which states that given a specific volume flux of sediment, the speed of the dune is inversely proportional to the height. And that derivation comes essentially from this sort of graphical consideration, where within a single time increment, a dune crosses through space this parallelogram of material that is directly proportional to its height as well as the speed at which it moves. Now, looking back at our power balance, we can see that we can find this term back into this equation. So we see that we have height and migration rate. So those can be essentially replaced with the volume flux of the dune. So what this equation is essentially saying is that based on purely geometric considerations, we can state that the wind speed is directly proportional to the cube root of the volume flux of the sediment. And obviously that's something that we can test, right? That's something that we can measure in real life and see if this is correct. So I made a short little plot. So on the x-axis we have the wind speed, and on the y-axis we have the wind parallel volume flux of the dune. And the trend line seems to link up quite well with this wind speed to the third power. So this is actually a really nice fit. Now it is a little bit challenging to get really accurate wind speed estimates from these super remote desert areas. So this graph is obviously not very high confidence, but it does show you that these geometric considerations are really effective in determining useful relationships that you can measure in nature. And so we're already a big step closer to our final goal, which is to predict the speed of a dune based on its shape. But to get a little bit further, we need to look further into this efficiency measurement. So the efficiency, as I said previously, is basically the percentage or the proportion of wind power that is converted into the mechanical power of the dune. And as I'll show you, this is also proportional to the geometry of the dune. But this part is a little bit tricky to grasp, but I've made some nice diagrams to see if I can make it simple. So in this diagram, in the top, you see a very tiny dune that is comprised of a couple dozen of sand grains. And let's now assume that this dune is moving from T1 to T2. It's moving 1 grain diameter of distance. And in this particular case, the windward side is twice as long as the other side, the leeward side, that's facing the direction of motion, right? So this dune is moving from left to right, and this left windward side is twice as long as the right side. Now, on satellite data, we can see that these dunes have very similar uniform shapes that can stay uniform. They stay the same over many years of time, many kilometers of distance. So let's work under the assumption that the shape of this dune remains the same as it migrates. So based on the difference in the amount of sediment that is on the windward side as compared to the leeward side, we basically have to conclude that only half of the grains that are moving up and over the brink of the dune can actually end up in front of the dune, right? The other half of the sediment has to be lost from the system somehow, right? Maybe it gets blown away through the sides, through the points of the bark end. Maybe they get suspended into the air and gets moved across the dune field. But we have to conclude that if the shape of the dune remains constant, only a proportion of material that comes from the back can end up on the front, right? Otherwise, the front would advance faster than the back, and the dune would actually decrease in gradient as it migrates. So the amount of sediment that is lost is directly proportional to the ratio of the windward side and the leeward side. So in this case, this ratio is 2. So the efficiency, you could say, is 0.5, because all of the material needs to get pushed up by the wind, but only half can actually contribute to the mechanical motion of the dune, right? So the efficiency when the windward side is twice as long is 0.5. And we can show that in this equation. So basically a steeper dune is more efficient, converts more wind energy into mechanical dune energy, than a shallower dune. And this proportion can be exactly determined by the equation of sine of beta over the sine of alpha. Right, so essentially a steeper dune has a higher efficiency. So I hope that's a little bit clear. Now, if we add that concept into our earlier equation for the wind speed and the volume flux, then we get the equation that's at the bottom right here. Now, another thing that we have to do before we can estimate the speed of the dune from its shape is to link the volume flux to the shape also. And in order to do this, we have to combine Buck-Knowles principle, so the fact that the volume flux is equal to the height times the speed of the dune, with the earlier surface to volume ratio principle, which we know contains this sine of beta, right? So by combining these, we can see how Q, so how the volume flux is related to the speed of the moving sediment times the grain size, multiplied by a trigonometric identity that involves the steepness of the dune, right? So this is basically just an algebraic combination of these two basic principles. So now finally we have all the ingredients that we need, or almost all of the ingredients. So the top equation is the power balance. It shows you how the wind speed is related to the volume flux of the dune. The equation in the center is how the volume flux relates to the dune shape. That's the one we derived in the previous slide. And we can combine these to develop an equation on how the wind speed determines the shape of the dune. Right, and what we see is that the wind speed is related not directly, but within this equation has a factor of speed of the sediment, and it has a trigonometric identity. Now, it can obviously be assumed that as the wind speed increases, the speed of the moving sediment must also increase. Right, and you can also see this from this really nice video. So you can, during a gust of wind, we actually have more grain-to-grain collisions, and that puts more grains into suspension, and it actually increases the total average speed of all these little sand grains. So we can actually develop this equation even further if we manage to relate these two factors to each other. So what I'm talking about is the two factors in red, which is the wind speed and the average speed of the moving sediment. Now, fortunately, there's been a lot of work on this, and sort of the consensus is that there's a direct relationship between these two. Now, if we assume some sort of relationship, so let's assume that this is linear, for example, then we can say that a higher value for wind speed should increase this trigonometric identity, right? So we must get some increase in this sine of beta, and that's exactly what we see on satellite images. So regions that have relatively low wind speed, like the Barkhan on the left, these are relatively shallow dunes. Now, as the wind speed increases, the trigonometric identity has to go up, and it's mostly controlled by the sine of beta. So actually the windward angle has to go up also. So in regions where the wind speed is very, very high, like here in the Namib Desert on the right, we can see that the dunes get this very sort of steep and broad shape. So the shape actually is determined by the wind speed. Now, another really nice demonstration of this is if you look at Martian dunes, because on Mars, the wind shear is very, very low. So Mars has a very weak atmosphere. And that results in these extremely low gradient Barkhan dunes. So that's an indication that these equations, these geometric equations that we're deriving, have some universal properties, right? I mean, geometry basically happens everywhere, equally on Mars as it does on Earth. So it shows you that we can use these equations across a really broad range of different environments. Now on the right, you see the dynamic dune field. And this figure just has a couple of different dunes visualized, just to show you that that within a single dune field that has let's say, a uniform constant environment, the angles of all these dunes are roughly similar, right? So it's really the environmental controls that dictate the angle of the dune. Now, to test the theories, so to see if these particular trigonometric identities that come out of these equations are actually valid in nature, I measured the speeds and the sizes and the windward angles across 9 different dune fields on Earth. So these are all Barkhan dune fields. There's a specific reason why I use Barkhan dunes. It's really because Barkhan dunes are sort of isolated and distanced from each other, so they don't really collide. They don't really interfere with each other in terms of the wind. And also, Barkhan dunes, they have these really nice size distributions. So a sort of transverse dune field tends to have really similar sized dunes. So it becomes really difficult to validate your theory when all the dunes have exactly the same size and shape. So Barkhans are nice and diverse, and nice and far away from each other. Now, by using a little bit of simple trigonometry, we can actually calculate this angle, this beta, so the windward angle from satellite images. And the reason for that is because the angle of repose, so the forward-facing angle, is really constant in these systems. So it's generally measured to be roughly 34 degrees. So obviously, if we know the angle at which the forward-facing side sits, then we can calculate the height using this top equation here. And we can use the height to calculate the windward gradient by basically using an inverse tangent function. So that's really nice, because this sign of beta shows up in all our different equations. So if we can actually measure them, then obviously we can use that to validate the equation, right? Now, and one really nice piece of validation is that we universally, wherever we go, whether it's Mars or any desert on Earth, we find that the volume flux is indeed correlated to the angle. So as the wind goes up, the wind power increases. We know that the volume flux must increase. And as the volume flux increases, the windward angle increases. And in the plot you see on the bottom left, you can see that this relationship is very, very nice. It's very universal, and it exists even within dune fields and also across different dune fields. So that's quite exciting, because then we can actually use that. We can use measurements of the windward angle to predict or estimate the volume flux. And from volume flux, we can actually estimate the speed of the dune. So like I said previously, there's been a lot of work on how to link the speed of the moving sediment to the wind speed. And that's actually another ingredient that we need to complete our equation. So the sort of modern consensus on the relationship between the speed of the moving sediment and the wind speed is that the sediment basically moves linearly as the wind shear goes up. So the reason for that is very, very complicated. There's been maybe hundreds of studies on this, but this is quite thoroughly tested and validated in the field. So by essentially estimating sort of simplistically that we can replace C, we can replace speed of sediment with the wind speed squared multiplied by some constant, then we can use the previous equations to develop our final magic trick super equation, where we can link the shape and the size of the dune directly and universally to its speed, right? And that equation is shown on the bottom left here. Now, obviously, there are more factors involved. So if you look at the equation, then you have one fudge factor. So this is value for d. It's sort of a scaling parameter, right? It's something that we don't really know. It can be any value, but we're going to derive this from the measurement, right? In terms of the other things, so the grain size, the gravitational acceleration, the density of the sediment, the density of the air, all these things are really constant throughout the Earth. So these values that we're going to use are simply characteristic values that we keep constant across all our estimates, right? So then if you have all these values and you parameterize your value for d, this constant scaling parameter, then all you need is a measure of wavelength, which is all the way on the right of this equation, and a measure of beta, so the angle of the windward side. And those two measurements are enough to essentially tell you how fast the dune is moving. And obviously we have to compare that to real measurements of the dune speed. And that can easily be derived from time series. So this shows you a time series of moving sand dunes in the Namib Desert. And if I sort of toggle in between two satellite photos, I can show you that these dunes are clearly displacing, right? So we know when the satellite photos were taken, and we know how much displacement there is. So we can actually calculate the speed of motion and compare it to our prediction. And eventually we end up with a super nice prediction. So our magic trick worked very well. You can see Gandalf is very, very happy with our result. And it shows you that, in fact, the geometric considerations that I've been trying to explain to everyone this talk are actually remarkably consistent, right? And they're really, really, this result, so this really accurate prediction, really gives me a good confidence in this idea that these geometric principles are accurate and very, very important, right? Now, one short thing that needs to be mentioned here is that all of this are averaged values. So obviously the speed, the wind speed, the speed of the dune, all of this changes through time. But in order to sort of equal out all of the random fluctuations and turbulent variations, I use averaged values. So averaged values for the speed of the dune, averaged values of the windward side across the dune field, and then unique values for the wavelength of each dune. So here you see the same data, and each squiggly line here is a dune field. And each node on the squiggly line is the speed of a dune. And they're basically arranged from smallest on the left to largest on the right. So basically we have for each dune field, a characteristic speed, and then the variations within that dune field based on the size. Now, if I superimpose the prediction, so these are measured values. If I superimpose the prediction, that you can see that it's very accurate, right? So the predicted values line up very, very closely with the measured values. Now, just to show you that this is not trivial at all, I've also made some plots of the exact same dunes, but this time I've compared them to other factors. So the plot on the left shows you the relationship between the wind speed and the speed of the dunes. And there's absolutely no correlation whatsoever. So this prediction of predicting the speed of a dune based on factors that you can calculate is not as trivial as you might think, because it's obviously quite expected that faster wind speed would lead to faster dunes. But this is completely not the case. So we cannot use these sort of intuitive relationships here to determine what's going on. We really have to go through all these steps of complicated geometry and trigonometry to figure out what is actually going on. Because if we compare these exact same dune fields to this relationship we determined, so the wind speed and the angle, then we do get a really nice correlation, right? So there's no trivial natural relationships between the sediment dynamics and the dunes dynamics. It's really sort of complicated geometry that's controlling this system. Now there's a little bit more evidence that helps sort of support this idea that the shapes of dunes are determined by surface to volume ratios. And it sort of comes from a little thought experiment. So let's say we have a dome-shaped sediment mound. So these do actually exist in nature. They're sometimes called dome dunes or proto-dunes. But you can actually split this shape into different segments that each have their own surface to volume ratio. And what you'll find is that the fringes have a higher surface to volume ratio and should outpace the center. So you get this sort of U-shaped Barkhan geometry. Now you can do the same thing for the vertical cross-section, and you'll find a U-shaped vertical geometry. And also you'll find that the top outpaces the bottom, so that we need to have this over-steepening and this cascading of material towards the front of the dune. So if we combine both directions, then we get this, we really approximate this well-known Barkhan shape very closely by simply invoking this surface to volume ratio idea. So what I've called it in my paper, I call it the moving graphs, because in a way that's sort of what they are. The relationship between the migration rate of the material and the surface to volume ratio is the same relationship as the one that is determining the parabolic shape of the Barkhan. That's essentially what I'm saying. And I really have high confidence in this idea. Not just from this thought experiment, but I also developed measurements from other dune types which support this. So in this compilation, you see 4 different dune types. So we have Barkhan dunes on the left. Those are the fastest dunes in this dune field. And then as the dunes get more amalgamated, they get lower surface to volume ratio. So their speed actually uniformly decreases. And you can see that in this plot. Now, what's even more amazing is that if we include parabolic dunes, then we find a completely mirrored relationship. So instead of faster parabolic dunes being smaller, we actually find that small parabolic dunes are slower. And as expected, by this geometric relationship, we can find the mirroring of this relationship in the mirroring of the shape of the parabolic dune as well. So the fringes outpace the center in the context of a Barkhan dune, but in the context of a parabolic dune, where this relationship of speed and surface to volume ratio is mirrored, we get the fringes actually lagging behind the center. So we get a completely mirrored shape of the dune also. So this is a little bit of a counterintuitive result, and it takes a while to sort of wrap your head around what's going on. But what I'm essentially saying is that the link between the size, so the surface to volume ratio, and the speed of the sediment is the same for different dunes within a dune field, but also for the shape of the dune itself. Now, if you take this even more further, you can actually explain the bedform stability paradigm as well. So on the top, we have a simplified version of the equation that we derived that links the wind speed with the angle of the windward side. So all of the different things, the density gradient and all these different things, we basically condensed it down into one constant, which we call x. And if you do that and you plot this relationship, then you find that as the wind speed increases, the windward angle goes up. So we have this initial regime of ripples and dunes that will become steeper and steeper. Now, eventually they become too steep as the windward side goes beyond the angle of repose. The wind basically becomes eroded. And that's when, in the context of this bedform stability paradigm, we enter the upper plane bed. So this zone of currents velocity that is so high that really no bedforms can exist, and you go back to a flat geometry. Now, the specific characteristics of that trigonometric identity that is related to this equation show you that it actually enters the domain of being shallower than the angle of repose in the negative part of the graph. So what that shows is that if we have this very high current intensity, then we have a situation where the windward side is negative. And that's a little bit sort of difficult to understand. But potentially that could, if you plot that into the equation on the top right, then you see that that's consistent with backwards motion of the bedform. So yeah, this has not really been tested yet, and this is really sort of speculation. It's a bit of a hypothesis that I'm trying to develop a little bit more. But it's an interesting concept that this geometric idea is also consistent with our understanding of bedform stability. So here's another very short explanation of what I'm trying to show here. So if we have zero current, then we have zero angle beta. So we have a flat bed. So if the current intensity increases, then the angle of beta will increase. So you will develop bedforms. Now, eventually, the angle of beta goes beyond the angle of repose, at which point the bedforms cease to exist, but actually continues theoretically onwards as the current increases even more, to end up eventually in the negative domain, where the bedforms are not too steep, but are actually moving in the wrong direction. So they actually have a negative migration rate. Now, again, this is sort of speculation. I haven't really tested this, but it does appear to be consistent with our understanding of how bedform stability develops, right? So what I'm saying is that basically these geometric principles, they run parallel with our fluid understanding of how this works, and they can actually form a single consistent framework potentially. Okay, so that's the end of the talk. So I'm excited to hear if any one of you has some questions. So if you want to learn more about the specifics of this theory and these ideas, then you can already read the preprint on Earth Archive. There's a lot of things that I had to gloss over in this presentation, of course. So the relationship between wind shear and wind speed and all these things. There's some subtleties that are actually really important, and they're much better explained in the paper. So if you really want to look into some of the details, then you're very welcome to read the preprint. Another very short notion on a little bit of advertising. So just to show you this really nice publication that SCPM has launched. It's the Sedimentary Record. So it's a fully free Diamond open access publication where you can submit all your amazing sedimentary geology research. We have a very, very specific vision of how to publish your work, and we think that this is a really nice venue for sort of these ideas that show up after a PhD project, right? You might not want to publish it in geology or something really, really sort of rigid and strict. It's sort of a little bit more of a lenient platform where we publish some really, really cool works that are related to any sort of sedimentary geology. So here's a couple of examples of some of our recent papers. So just to point this as a point of attention to people that haven't heard of it, the sedimentary record, very cool publication by SCPM.
All right. Thank you very much, Dan. That was really interesting. Very cool concept. So the chat is open. So if anybody has any questions, please feel free to type your questions into the chat and make sure you say who you are and where you are watching from. We already have a question in there. This is from Yako in Bangor, Wales. Excellent presentation, clearly explained. 2 questions. 1, what kind of UW is predicted? Height, average speed, or speed at a certain height above the bed? And 2, can this model also be used for subaqueous bedforms?
Oh, thank you very much. Very cool to be talking to Jacco, which I've been reading a lot of his papers in order to make this work. So so it's quite cool to be talking to you. But yeah, this is a very good question, and I knew this was going to come up because it's something that I really didn't go into in this presentation at all. Because obviously wind speed is not constant from the bed, right? It increases as you go up from the bed. So what I'm essentially doing is essentially UW is wind shear. That's what it comes down to. So it's a vertically averaged wind speed. And under many conditions, when you look at sediment transport dynamics that occurs really close to the bed, this is not really an appropriate equalization. But in this case, and I have some data to support this for sort of macro objects, so for things that are bigger than 3 meters tall, this does actually work. So, for example, in these wind turbines, also you can have a surface area that's a couple meters tall, or even 100 meters tall. The changes of wind speed between the bottom and the top really make no difference in this wind turbine equation. So when you're looking at macro objects, the vertically homogenized wind speed is essentially the same as the wind shear, or is essentially proportional to the wind shear. So I hope that clears that up a little bit. Now, 2, it says, can this be used for subaqueous bedforms? Well, the beauty about this geometric principles is that geometry exists everywhere, right? It exists just as much at the bottom of the ocean as it does on land. And we do indeed find barkhan dunes in any sort of setting, right? We find them at the bottom of the ocean. We even find snow barkhans in snow fields. So my expectation is that a lot of these equations are going to be appropriate for subaqueous settings as well. Although I have to admit that I don't really have the data to support that.
Cool. Very good. If anybody else has any other questions, feel free to post them. I might ask one. Do you think that you will try to apply this to any other types of dune shapes, or are you going to stick with barkhan dunes?
So the barkhan dunes work best in terms of validation. But I actually have a sort of, I'm advertising a master's project to work in a flume where we're going to try to do this in for transverse dunes, like small ones, like a meter or so. And my expectation is not really going to work because the dunes are transverse dunes are all interconnected lengthwise. So any sediment that is lost from the brink of one dune is immediately supplied to the next dune. So the train of sediment that you get is a different relationship than the one that I'm describing. Mm-hmm. So I think some modification could be done to still allow this to work somehow, but yeah, it does need modification for different types of bedforms.
Awesome. All right. Well, I think we'll probably wrap it up here. If anybody else has any questions, they can probably send you an email. and check out your paper, of course, to figure out what all the details that's going on. But thank you again, Dan, for a great presentation.
Okay, thank you. Thank you for hosting me. It's very nice.
Yeah, excellent.